All right, hello everyone. Here is a video describing how to work through Webster's method of apportionment. We've covered Hamilton and Lowndes so far. Those um, are calculated by comparing different decimals. Jefferson's we found was an interesting way where you change the divisor that's being used to figure out like how much representation per seat or how much per resource that you allocate. By changing that number, getting everything to work out without needing to assign extra seats. The difficulty, of course, with that was creating all of the breakpoints and everything. Um, Now, Jefferson's method was used right at the start in 1792. Based on the 1790 census, it was the first apportionment method voted in, and it was good for a while. Um, but things happen. Let's take a look at the 1820 census. So we are now 3 successful apportionments later, and we are getting ready for a fourth in 1822. The house size is set to 213, up from 181. Now, this may seem like a lot considering that it started at what 65 in the Constitution and then was 105 right after that. Um, so it seems like a lot, but what's happening is they're just adding seats to ensure that up to the minimum number needed to ensure that nobody loses seats. So this number was chosen. It's the first number where nobody loses a seat. Everybody gets to keep at least the seats that they have. Okay, and that's tricky to do because there are 6 new states. Um, so basically, you're adding 32 seats, and a lot of that is because of 6 new states that are being added in the 18 teens. Um, a lot of those Midwestern states. Missouri was just becoming state. So we're talking states like Indiana, Illinois, Michigan, those sorts of states. Okay, so let's take a look at the data from the 18. This is the 1820 census. And here are the 5 most populous states. First thing you're going to realize is New York has quickly overtaken Virginia as the most populous state by far, actually, 30% difference between New York and Virginia. Um, and Ohio is now the 5th most populous state, despite at the start not even being a state. Um, so interesting values here. Again, magic number was 213. The initial quotas come from the divisor of 44,718.72. That was the original. So here's the initial allocation. And these numbers, I'm not quite sure. I think those are just how they round. If you look, these are just rounders in the nearest whole number. Initial values here for Jefferson's method, remember everything rounds down. But take a look what happens. Based on the whole data, Jefferson's method selected the divisor 42,500, a bit lower than the 44, we knew that. But look what happens. New York hits a breakpoint of 32. Wait a second, their initial was 30. How did they suddenly end up with 32? Well, that's really weird. Like, why would they need more than one extra seat? Why would any state need to get more than one extra seat? Well, let's think about this. So the problem here that's happening is, oops, erase your problems. There we go. Nope. Okay. I don't like it's got that little eraser thing there. So what's happening is the other states, you look at this, we already know that Jefferson's method favors larger states. And the reason why it favors larger states is because it takes less change in divisor to equal a new state. And that's a less change in order to get the quota to move percentage-wise. That's why it always favors larger states. Like, for example, New York, to go from 30.6 to 31 requires like a 1.5% change in the divisor to get it to go from 30 to 31. Whereas a state like Ohio, to go from 13.0 to 14 requires 5%. So it makes sense that New York is going to pick up extra seats first. But two, well, let's look at the breakpoints here. 42,500. So New York's first breakpoint is at 44,200. Then look at the rest of them. 43.7, 43, 42.5. Looks like North Carolina just barely makes it. And then Ohio is at 41.5. So Ohio does not get an extra seat. It's below the 42,500. So, but why does New York get two? Well, it turns out, let's look at the breakpoints and how we calculate breakpoints. Okay, so to calculate breakpoints, we divide by n plus 1, right? So we take 1,372,812 and we divide by 31. And that will tell us, at what point it gets its 31st seat. And you're going to get that 44,200 number. But what they didn't realize at the time, what Jefferson, I don't think ever realized when he did this, and he knew that this favored larger seats, but I don't think he knew this. Obviously, it's impossible. I can't really ask him anymore. But but the census person didn't realize this. No one in Congress thought that this could happen. Everybody, when they did Jefferson's method, when the census person was checking Jefferson's method for the last 30 years, they would calculate the first breakpoint, and then that's fine. But here's the thing. Let's look at New York's second breakpoint. No one ever thought to calculate what happens, how much would it take to get 32 seats? And if we do that division, so 1,372,812, and we're going to divide by 32, you're going to get 42,900. So, and this is because New York has such a large population that and it has so much initial quota that the change in the divisor needed to make all these moves is very, very small. So 44,200 is good for the first, but then at 42,900, that quota has increased enough to go over 32. And therefore, and you can prove it by dividing the population by 42,500, and you'll get over 32. So, and you'll notice that 42,900, North Carolina doesn't even hit its first breakpoint until 42.5. So these are so close together that New York picks up 2 before North Carolina can even pick up 1. That is a problem. And yes, Congress favors larger states because larger states have more votes, and states with more votes are going to pass things with majorities. Yes. So methods like Lowndes' method, which favors small states, were never going to gain enough traction in Congress. Jefferson's method was liked because it favored larger states. But now we had a problem that we just can't get around. Now it's clearly unfair. And that's a problem. So what do you do? Could they perhaps just make a rule that says that they can only get one extra seat? I suppose you could make that rule, but that's not part of Jefferson's method. And Congress would actually have to vote on that. And it was a pretty bitter division at this point. Congress would have to vote for that rule. Now the South would vote for that at this point. Remember, this is, pre-Civil War tensions. So the South would vote for it. New York certainly wouldn't. They said, hey, we're due 32, you give us 32. So it kind of became locked in Congress. Okay? This is called a violation of the quota property. Jefferson's method does not satisfy this property. An apportionment that satisfies this ensures that no state is more than one seat different than its natural quota would suggest. Basically, what that means is that New York should only get 29, 30, 31. Ohio should only get 12, 13, or 14 based on this data, stuff like that. Clearly, that's not happening. So, what's the resolution? On February 13th, 1832, Congress discussed nearly a dozen different ways to apportion the House. As far as 1820 goes, they had to keep it. Congress could not vote, nor did they have enough time to discuss and come up to a vote to modify the apportionment method to change this, nor would they get enough votes from support from the big states to do that. So they had no choice. Had to stay. Another reason why the South was not too happy with the way things were going. So like I said, in the 1830s, this happened again after the 1830 census. And Congress realized that this was just going to keep happening. So they discussed nearly a dozen different ways to apportion the House, and they could get nothing to stick. It was, again, a deadlocked issue. Now, in 1832, this guy, his name is Daniel Webster, he's a senator from Massachusetts. There's a lot of stuff in New England that bears his name now. He steps in. Representative John Quincy Adams, who is the former president, the only former president, mind you, to go from the presidency to the House of Representatives, he suggests modifying Jefferson's method by rounding everything up instead of down. That would have the reverse effect by favoring small states. That didn't fly because the Electoral College already favored small states due to the fact that of the 2 senators that everybody gets. And he's from New England. New England's full of small states, so nobody listens to him. So he tells Daniel Webster, and he takes up the matter, and he ends up coming up with a new idea. And it's kind of a pretty self-guiding example, if you will, kind of the obvious conclusion to all of this, that he gets passed for 1840. Well, Jefferson rounds everything down. That doesn't work. It's biased. Can't round everything up, because that's biased the other direction. So what do you do then? Easy. You round everything at the middle at 0.5, just like you do in school. Why didn't anyone think of that before? Webster's method. Find a suitable divisor such that when applied, all quotas are rounded to the nearest whole number. The correct number of seats is a 1. Whoopsie. Now a straight line. So the key here, nearest whole number. All right, so what does that mean, nearest whole number? Obviously, that means up and down at 0.5. So that means, unlike the other methods, when we go to calculate quotas, we're just going to round everything to a whole number. What that's going to do is, you might wonder, well, is that still going to favor large states because large states tend to round up, like Hamilton does? Yes, But what's going to happen when you do that is a state that rounds up is going to balance with a state that rounds down. And that means that there's a seat that doesn't have to be allocated. Interesting. So two seats, one that rounds up, one that rounds down, instead of their decimals adding up to 1 and causing an extra seat to be needed, they'll cancel each other out. Because again, when that extra seat is generated, who does it go to? It's going to go to the bigger states, right? So this prevents those extra seats from getting generated, or as many of them. Interesting. So let's see. This is one of the fairest of all the methods. The other big part is because we have less seats to deal with, the divisor is always closer to the original divisor than Jefferson's. I'm going to put almost always because I can't really prove that it's always closer. But as you'll see in the examples, it is definitely closer. Quota property violations can happen, but on the order of less than 1%. And you have to have one state that's like more than 40% of the total for that to happen. There is one disadvantage, though, as you're going to see. Because we're rounding to the nearest integer, which could involve rounding up or rounding down, in this case, you could end up assigning in your initials too many seats rather than too few. And we're going to see an example of how that happens and how to deal with that. But it shouldn't be more than common sense allocation, but we'll make sure we do an example of this. Okay, let's go for it. Suppose that Minnesota's 9 electoral votes in the 1892 election are apportioned based on popular vote rather than winner take all. Interesting. This is interesting. So apportion the electoral votes in each state. Fascinating. I wonder what would happen if we applied this to current elections. That'd be kind of fun. Okay, so let's give you a little bit of background on this. We're going to obviously need to do some math. We're going to need some divisors here, and we're going to need a little bit of help. So the first thing that I can do is we can go ahead and add some of these values together. 100, 589, 122, 736, 33.99, 14,117, and that gives me 267,841. Okay, 267,841, and we're going to divide by 9. So my divisor is going to be 29,760.11. Because it's already a 5-digit number, I'm not going to worry about needing the extra like 4 decimal places here. Okay, so we're going to do quotas. All right, so when we do these quotas out, again, just be careful that when you do your initials, we're going to round it to the nearest integer rather than rounding everything down. Okay, so we're going to do our division here. So 100, 589 divided by 29,760. So 3.3800. Okay. So what I like to do, 29,760.11, add that to the memory. So we have that, and then I can just do 122,736 divided by memory, 4.1242. Oopsie. And then we'll do the same for the others. Divided by 1.0215 and 14,117 divided by um, 0.4744. Okay. Oh, it's a 0. So we will have an initial value of 0. Hey, that's fine. Okay, notice all of these decimals are in fact lower than 0.5. So just like Jefferson's, they all will round down. Hey, you know what? That's okay. That's going to happen. And we're going to have exactly 1 seat left to award. Now, even though that works out the same as Jefferson's method, the breakpoints are going to be different. Okay, breakpoint formula. Here's the thing. Notice that now we're rounding to the nearest integer. We want to know when this is going to reach 4. But now under Jefferson's method, the quota has to reach 4 for the number of seats to get to 4. But is that true if we round? No. When we round, what number will round up to give us 4 seats? 3.5. So what's going to happen is if this quota value is over 3.5, then this is going to reach 4. So instead of needing this to go all the way to 4, we just have to go to 3.5. So to calculate the breakpoints, we are going to do population divided by n plus 0.5 rather than 1. Because the difference now in the allocation is going to happen at 0.5 rather than at the whole number. And so because these numbers all get rounded down, you can just simply add the 0.5. So 3.5, 4.5, 1.5 would go to 2, and then 0.5 would go to 1. So let's go ahead and do that. So I'm going to do each population and divide by allocation plus a half. So 100, 589 divided by 3.5 gives me a breakpoint of 28,739.71. Okay. The next number that we're going to use is we're going to divide by 4.5. So we're going to do 122,736 divided by 4.5. 27,274.67. Okay, and then finally we'll just do the same for the others. 30,399 divided by 1.5. That's 20,266 on the dot. And then finally 14,117 divided by 0.5. And that's 28,234. Okay. All right, so now that we've calculated those breakpoints, now again, the question, just like with Jefferson's method, when do we get the extra seat? We need 1 extra seat to bring this up to the 9 electoral votes. And which one's going to get it? Well, the one with the highest, right? Closest to the original divisor. And in that case, that's going to be Grover Cleveland. So my final allocation is going to be 4, 4, 1, and 0. A 0, is that safe? Yes. Think about it. We're assigning electoral votes. Mr. Bidwell here did not get a lot of votes, 14,000. So maybe that's just not enough of a vote in order to get any electoral votes. Think about having your secondary political parties, your third-party votes and whatnot nowadays. They don't get any electoral votes, but they get votes. They get popular votes, but not electoral votes. Same situation here. Okay, so in this particular case, Grover Cleveland gets 1, so it's 4, 4, and 1 for Mr. Weaver. Okay, and then finally, what divisor would we choose? Well, like before, we have to choose the divisor that's in between the last breakpoint that we need and the first one we don't. So it's got to be below 28.7 but higher than 28,234. So what could we use? 28,500, nice and easy number. So we're going to set divisor to 28,500. Now you might be curious as to what the Jefferson divisor would be for this one. The Jefferson divisor for this one would be, let's see, I have that value right here for you. Jefferson divisor, 25,000 is what this one would be good for. So 25,000. You want to change this to a 9? Yeah, it would be exactly 25,000. So in this case, so the Jefferson divisor, I'll put this in purple up here. 25,000 is a fair amount lower than this. It is over 10% lower. Whereas the Webster divisor is much closer to the original 29.7. So having a closer divisor means that you're applying a rule that's much closer to the true breakdown of the population that's in the state. And that works, and that's quite lovely. Okay, so this works out very similar to Jefferson's method, right? And the only difference with this one is having to use n plus 0.5 in the breakpoints rather than plus 1. That was the only difference. Okay, let's do this problem again, but this time, because under Webster's method, it's possible to get too much allocation. Let's see how that plays out. All right, so we're going to go kind of quickly through this one since we've already done some of the legwork. The numbers will definitely be different, but we can see how this happens. So let's say we go to a state with 15 electoral votes. Let's use the same numbers, just for the sake of argument, even though obviously the state would probably have more voters. But let's say we do 15 electoral votes instead of none. Let's see what happens. We're still going to add it up. We're going to get the same number of, 267, 841. That's not going to change. But the divisor is going to be different, right? So 267, 841 divided by 15 is 17,856, 0.07. All right. Let's do our quotas. And you know what? For this particular case, I'm actually not even going to look at the quotas. I'm just going to put, my initial values directly in. Okay, so we're going to put our initial values directly on. And so I'm going to say initial, and we'll just show it right from here. So let's do, let's take that number and let's clear memory, add that to memory. Okay, so we're going to do 100,589 divided by new divisor, 5.6333. And so what's the initial? It's going to go directly to 6. And then we'll do the same for the others. 122,736 divided by 6.873. That's going to round to 7. 30,399 divided by that number. 1.70, so that's 2. And then finally, 14,117 divided by 0.79. So again, that also rounds up, and that's going to round up to 1. Okay, so when we do this out, all 4 numbers round up, which is interesting. And because all 4 numbers round up, you have 13, 14, 15, 16. 1 seat too many, which means we have to subtract 1. So that means that one of these is going to lose a seat rather than gain. So how do we do this with the breakpoints? Well, remember that we're not adding anymore. We have too many seats. We're going to lose a seat. So in this situation, we want to know what must the divisor be in order to take this sixth and bring it back to 5. Well, to do that, that 6 is going to have to come below 5.5. So to do that, we're going to subtract 0.5 rather than adding 0.5. So when we do that, your breakpoints are actually going to get higher, as you'll see here. So we'll do 100,589 divided by 5.5. That's going to get me 18,288.91. So the divisor is higher because remember, if lowering the divisor increases seats, increasing the divisor lowers the seats. Let's do the same for the others. So 122,736 divided by 6.5, 18,882.46. And then 30,399 divided by 1.5 is 20,266. Sound familiar? That was the same number as the other one. And then the same thing is going to happen here. 14,117 divided by 0.5, and that's 28,234. So just like before, in order for Bidwell to get their second seat, they're going to have to go all the way to, or sorry, in order for them to drop their seat, they'll have to go all the way to 28,234. Okay, so it's the same break point as we had the first time, but from a different perspective. Okay, so now once again, we have to lose one. Which one are we going to lose? Now you might say before the 28,234, that's the highest, right? But think again. Remember that the breakpoint, that when we move from the divisor, we always move from the divisor either up or down. So the one that's going to go away is always the closest to the divisor. And that's what I said before in class. I said that even though, we're always picking the highest divisors with Jefferson's method, you have to remember that it's always the closest to the divisor. You don't want to change it as much. So which one's going to lose the seat? It's going to be Cleveland. Is it? No. It is, in fact, yes, it is going to be Cleveland. 18,288 is the closest to the 17,8. But we then don't want to lose another seat beyond that. So much like before, we're just kind of thinking about it in the reverse. We want Cleveland to lose a seat, but the next number, Harrison, we don't want to lose a seat. We're only trying to lose one seat. So we want to keep these, we want to keep these, we want to keep these. That means we want to choose a number in between there. So let's choose 18,500. And my final allocation is going to be 5,721. And that's going to add up to 15. Now, when I go and look at my spreadsheet, I'll show you this way the spreadsheet looks on this. By the way, we are almost ready to start working on this one in class. If I scroll over, if I look at Webster's method, if I change this to 15, my house size is 15, and my Webster divisor here, let's make this a little bigger. Actually, you can probably make it bigger on your own screen. Let's see how they compare. Jefferson's method, 15,000. Oops. Should work as a divisor, but it doesn't. That might be a case of the quota method problem happening. So let's figure that one out. So 5610. Yeah, I believe that's a case of, yeah, that it looks like it's a case of the um, issues with the breakpoints. Because, yep, you're going from 6 to 8. Quota issue, so 15,000 doesn't work. Let's do 14,500. That one still doesn't work. 14,250. That looks like is a problem. Okay, so we're gonna have to toy around with that one. Okay, so 15. Still maybe. Okay. I'm gonna have to toy around with that one. Okay, but let's look at some of the other ones here. So I wonder what 15. Yeah, 15,200 works, but we'll get to that. I'll have to fix that later. Okay. Um, So in this particular case here, so Webster divisor, 28,500. No, so as we said before, 18,500. That one certainly works. Okay, and you'll see that 18,500 works. The Jefferson divisor are much different than the original. Webster, not so much. Okay, I hope that, and we'll see 5721. Okay, folks, I hope that does it for you. So again, let's just take a look here. Be careful. You may choose either negative 0.5 or positive 0.5, depending on whether your breakpoints go up or down. All right, and I hope that that kind of explains the difference between the two that you could see. The good news is this basically covers everything. Any other apportionment methods that we do are pretty much exactly the same as this, just maybe slightly different formulations. So as long as you understand the difference between when to go up and when to go down, I think you'll do pretty well with this. All right, folks, have a lovely evening, and I'll talk to you in class.